working.
Okay, so this is a contrail. You may have noticed these before in the sky, and they're one of the most visual impacts of aviation on the environment, particularly on climate change. These contrails are formed on particles emitted by aircraft engines, and it's water vapor that's emitted by the engine as a result of combustion, and also water vapor in the ambient environment that condenses onto particles, forming these initial particles which then very quickly freeze, or ice crystals. And what we see here is the ice crystal cloud persisting at least for a fraction of a second in this image. Wait. But these contrails can, under the right conditions, persist for several hours. So this is an example here of a military aircraft doing an exercise over the east coast of the UK. And the sort of contrail was visible in satellite images, and over a series of hours, that contrail vectored with wind. It persisted, which meant it didn't dissipate or sublimate or disappear. And it actually got sort of sublimated, or it got merged into other ice cloud, high-level cirrus cloud, and advected all the way over to the southeast of the England. So it's these persistent contrails which are the most climatically important. They block outgoing long-wave radiation from escaping the Earth's atmosphere, and they can also reflect incoming solar radiation, and in that way have a cooling effect and also a warming effect. So during the night time, the effect on net is warming, and over the world, over the year on average, the average effect is a warming effect that's similar in magnitude to the radiative effect due to aviation CO2 emissions. So it's a really significant climate effect of aviation. What this project is looking at is this very early stage, so right up here, where we're forming the emissions are being ejected out of the engine and the contrail ice particles are forming. So what particles are acting as their seeds for contrail ice particles. The sort of understanding has been that it's on non-volatile soot particles, and that there's a good correlation between the number of ice particles and the number of soot particles. And in this work, what we're looking at is whether there's the potential for other particles to start to play a role, particularly as you reduce soot particle emissions. Okay, so this video on the left, there you go, shows some contrails forming over imperial, and you can see that there's a dependence on the weather conditions because some of them persist and some of them don't. There's also dependence on what aircraft it is, what altitude it's flying at, and some of these contrails persist for only a few seconds, and some of them you see lasting for minutes as they advect across the frame. Global aviation, if we kind of zoom out a bit, global aviation contributes about 3.5% of net effective radiative forcing. Anthropogenic radiative forcing and non-CO2 forcing contributes about 2/3 of that. So very different to other sectors where CO2 dominates the climate effect. For aviation, we have very significant components of warming due to these non-CO2, majority of that down to contrails. This is a schematic of the process I was explaining, where we have emissions from the aircraft engine. We might have some condensed matter, so maybe semi-volatile organic material that coats those particles, maybe it's sulfur. We then have condensation of water onto those particles and then freeze them. So we expect about 10 to the 11 to 10 to the 16 particles per kilogram of fuel burned, and that's very dependent on the engine technology that's used. Modern engines can get down to 10 to the 11, but older engine technologies are emitted at 10 to the 16. So that wide range of magnitude in terms of number concentration of particles, we expect to have an effect on the properties of the contrail that persists, because it affects the number of ice particles that are in that contrail. But is non-volatile particulate matter the only particle type that we should be considering? And this was the topic of this project. And this is important because there's incoming regulatory changes. we already have regulation on non-volatile particulate matter of aircraft engines. In the midterm, there might be scale up of the adoption of sustainable aviation fuels and lean burn engines, which significantly reduce the soot particles and non-volatile particles coming from engines. And in the long term, we might have the introduction of new engine technologies such as hydrogen, where we wouldn't expect there to be any carbonaceous soot particles. And so could there still be a source of particles from those engines that might act as seeds for contrails? And we really don't know where we lie on this graph here, which is showing how the ice particle concentration in the contrail depends on the soot particle emissions. So we're kind of up here now, where there's a one-to-one relationship pretty much between the number of ice particles and the number of soot particles. As we reduce soot particles due to engine technologies and fuels, what happens here? There's sort of two realities that could take place. One where the contrails aren't forming because they don't have particles onto which to seed, and up here where we have a large number of other types of particles and the contrail still exists. So this is sort of where we're interested, and there's some interesting sort of in situ measurements showing that we could be up here. And what we wanted to do with this study was show whether we could form ice particles on lubrication oil. Lots of studies have quantified that lubrication oil does come from aircraft engines. We need lubricants in the engine in order to keep it so it doesn't explode, to keep moving parts able to move. It's emitted through vents. It's also emitted. So depending on the engine type, it could be emitted in a core, it could be emitted in a separate vent. And so this is a kind of picture of what's happening in an aircraft plume. We have gaseous vapors that comprise those vapors that come from lubrication oil that might be heated up and evaporated, renucleating into new particles as that plume cools down and dilutes. And in the far field, if you were to measure concentrations of particles near an airport, if you're sort of a few kilometers away, the dominant mode is these semi-volatile nucleated particles. So there's a really significant contribution. We just don't know exactly how they act at cruise. So this was the experiment. We had a method to generate oil droplets of around about 100 nanometers in diameter. We used a SMPS to measure the size distribution, and we put those particles into an expansion chamber called the portable ice nucleation experiment. And what this does is it charges up, it cools down the aerosol, and then has an expansion cycle where the pressure reduces, the temperature reduces, and we can get activation because the relative humidity increases. This is what a typical expansion looks like, where we have the sort of start of the experiment here, and then the expansion. So one of the ends is closed and the other end is pumped out. And then after about 10 seconds here, we're starting to see within the optical particle control line chamber, each of these dots represents a particle measured. And we're seeing this sort of burst of particles form as oil droplets are being activated into water droplets. So as we continue through, the temperature is decreasing, the pressure is decreasing, and we're seeing a concentration of observable particles that are several microns in diameter. When we do each of these experiments, we can map that onto the temperature that we started the experiment at and the supersaturation of that experiment. And we can do that for different starting positions, different starting temperatures. And we aggregate those with similar starting temperatures to get these points over here with the error bars. So what this is showing is that as we decrease the temperature, we need higher supersaturations in order to activate those lubrication oil particles into droplets. And that's consistent with what our understanding of the physics is. But when we start to compare that against other types of particles, we can then start to relate how active lubrication oil particles might be in relation to soot particles. So soot particles on this, so our lubrication oil particles are here. For table salt, we expect it to be, so what we're doing here is characterizing the hygroscopicity of these particles, how able they are to take up water. And relative to these other two compounds, table salt and alpha-pinene, our lubrication oil particles are not as hygroscopic. In fact, they don't like to take up water. But these supersaturations are easily achieved within cooling and diluting plumes of air. So we could still activate these lubrication oil particles, even though they don't like to be activated as much as some particles do. So when we compare them to subparticles that would preferentially activate first, and that's why we're seeing the behavior that we do see at rich conditions where we have lots of subparticles. They seem to activate first, but once we get down to lower subparticle concentrations, we would expect to be seeing activation of lubrication. But they're kind of in competition, and the subparticles are preferential. They have the advantage in that respect. And yeah, this is sort of complicated figure, but what this is showing is the supersaturation that we would expect to see in a cooling aircraft plume. And you can see it goes well above 200%, but it's well above the supersaturations we would need in order to activate these lubrication oils. We were also able to look at the freezing behavior, so whether the lubrication oil particle had any role in enabling the freezing to happen at a warmer temperature, so that would be heterogeneous nucleation of ice. This shows an example of size distribution that we measure when the chamber is warm, and we're seeing about 5 microns in diameter. Those are water droplets. When we cool down the chamber to 230 Kelvin, we're seeing a much larger mode of particles, and these are ice. So these water droplets, when we have colder temperatures, freeze, and then we have faster uptake of water onto the ice crystal, forming larger particles that we measured. When we have intermediate temperatures, we do see a bimodal distribution where we have some remaining as water and some activating and freezing into ice. So what we can say here is that there's a condensation process followed by freezing. We wanted to look at whether these oil particles are affecting the freezing mechanism. If we had heterogeneous nucleation of ice, it could mean that the ice particles are forming at a slightly warmer temperature than during homogeneous nucleation of ice. But our results show that that's not the case, that there's homogeneous nucleation of ice. So there's no role of those oil particles in, I'll use the word, catalyzing the formation of ice within the particle. And that's important because it helps us to understand that these particles are all likely to activate at roughly the same temperature. It's not like some particles will activate sooner than others. If you do that, you'll get different distribution of sizes of ice particles within the contrail, and that could affect its ultimate lifetime and rate of processes. So to summarize, the decrease in non-volatile particle emissions will lead to an increasing role of lubrication oil. And we've shown that through the experimental work that we can activate lubrication oil particles, and then they will freeze by homogeneous freezing. And this is going to be particularly important as engine technologies become cleaner and as fuels enable reductions in particle emissions too. Joel's continued to work on this, so he's going back to Leeds later this summer. He's going to use our soot generator to repeat these measurements using soot, but also to see if we can have mixtures of both soot and lubrication oil. And then we want to account for the role of lubrication oil in modeling studies. So how important is this in terms of the total size of the effect of aviation on climate change? Thank you.
Thanks very much, Mark. We have time for a quick question for our next speaker. Thanks very much. Really interesting talk. I guess given what you found in terms of homogeneous freezing, is then the total goal for manufacturers of these engines to reduce the overall particle number of any type? Is that what you conclude?
Yeah, so one engine manufacturer actually asked, what should be the target? And I think what this work is showing is that, yes, it's good to reduce subparticle emissions, but we also need to be aware that there's other particles that could play a role. And so what's the requirement in terms of, I think there's a requirement to start to measure these semi-volatile particles currently then not measured as part of the regulatory process. And that will drive technology developments and reductions in oil emissions. So that, there's technologies that are out there that can do that. So it shouldn't be without actually a brain possibility.
Thank you. Great. Well, thanks again.